Okay, so now that we've seen the basic idea of conjugate addition and some of the examples of that, I just want to briefly look at some of the factors affecting conjugate addition. And there are three main ones that we need to look at. The first is the type of the nucleophile that we are using in the reaction. The second one is the conditions of the reaction can be very important. And then lastly, the nature of the alpha-beta unsaturated carbonyl will also make a big effect in the why we get a conjugate addition versus, say, a 1,2 addition to the carbonyl. So let's look at what we mean by these three terms. So as we consider the type of nucleophile that influences whether we have a conjugate addition, which is adding to this carbon here, versus a 1,2 carbonyl addition, which is adding to this carbon over here, we need to consider a number of different factors. And actually, in terms of conjugate addition, this is probably one of the more difficult factors that you're going to have to learn about. Why it is difficult is that in a very simple sense, and I'll have to explain this a bit more, in a very simple sense, adding in a 1,4 addition is with nucleophiles that are soft, and adding to the carbon that's a carbonyl, nucleophiles do this, which are known as hard. And that's where the difficulty comes, is knowing whether we have a soft nucleophile or a hard nucleophile. Okay, so where do these come from? Well, this comes from the concepts of reactions, where there are two main factors that affect reactions. The one is charge, so we put that over there, and the other thing that affects it are orbitals. And both of these things are important in reactions. Orbitals overlapping to form new bonds, and the way they do that, and charge bringing two molecules very close to each other in order to react. And all reactions, these two factors normally have some part to play. It might be a large part or it might be a small part. But if a reaction is dominated by orbitals that are working together, then the reaction and the reaction partners are termed to be soft nucleophiles, and soft electrophilic position, like on over here. That's why we react over there. But if things are brought together by charge, then what's happening there is we're normally seeing like pluses and minuses, which are bringing things together. So if we look at the unsaturated carbonyl compound that we have over here, the difference between these two positions here, this carbon over here, because it's next door to the oxygen, actually has a greater positive charge on it than this carbon over here. All right. So we can draw the resonance structure that seems to show there's two pluses on both carbons, but because this is bonded to the oxygen, it's much more positive over here. So this carbon is affected more by nucleophiles which are hard, which are charge driven. And the difference over here is that this carbon over here is driven by orbitals. Technically, in the language of frontier molecular orbital theory, this carbon has the largest coefficient in the LUMO. You can go and look that up in your textbook to read up a bit more about what that means. And so nucleophiles that are driven by their orbitals, not charge, will have a favorable overlap with this carbon, the LUMO of this carbon in the reactions, and so they tend to go over there. So the hard part is going to be to decide whether nucleophiles are hard and which are soft. And that's not terribly easy. Some are fairly obvious, like for instance something like an O minus is certainly a hard nucleophile. Something like Cl minus might be considered a hard nucleophile. Nitrile, charge driven, it's a hard nucleophile. Even just oxygen and alcohol would be considered a hard nucleophile. These are small atoms with charges on them. Something that's driven by orbitals are going to be much larger atoms. An example might be I minus, definitely orbital driven. Thiols are fantastic, these lone pairs of electrons there. Thiols are fantastically orbital driven nucleophiles and are brilliant at doing conjugate addition. And other atoms that you might see, for instance, phosphorus, phosphines, various other phosphorus versions, they are also so-called soft orbital-driven nucleophiles. And of course, there are going to be nucleophiles in the middle. For instance, amines, your primary and secondary amines. So an example is your primary is going to be somewhere in the middle over there. Br minus sits itself somewhere in the middle. And so there, it can be a little bit more difficult, and we have to look at some other reasons for why we'll prefer to go either to the beta carbon or add to the carbonyl carbon over there. All right, so you're going to need to follow this up in your textbook. There's a lot more depth to what I've just said over here, but as you just, it's just a bit of an introduction. As we grapple with this, you'll start to see much more of a pattern emerging. But let's look at the second factor now. So the second factor we're going to look at is the conditions of the reaction, and the formation of the cyanohydrin versus the addition of the nitrile in a conjugate addition to the unsaturated ketone is a very good example of this. Just by changing the reaction conditions, either we're doing it under cold temperatures or if we heat it up, we can affect the two different products. So what's going on here, it's fairly simple. The way that we control this is really pretty much to do whether a reaction is reversible. The nitrile is a hard nucleophile, and it actually does prefer to go to the ketone carbonyl. And so this reaction is dominated. But the thing is that this reaction itself is actually an equilibrium. And so that's a bit of a lie there what I drew out, and it is an equilibrium. So the reaction is fast, it goes there very quickly. So at low temperature we can control this through kinetics, and we can get this product through kinetic control. But however, this is the more stable product over here. And so if we have this in equilibrium, once this happens, even though it's slow, it's not preferred, nitrile is not a hard nucleophile. However, once it does add over here, this is a thermodynamically stable compound, and so this is the thermodynamic product. So this can only happen in certain circumstances. The reaction obviously has to be reversible. The question, of course, why this is more stable than this one over here is a very good question, and I'm going to task you to go and look in your textbook to find the answer to that. So the final factor that affects whether we get conjugate addition versus 1,2 addition has to do with the nature of the unsaturated carbonyl. And here I've just drawn out 5 representative examples of the types of carbonyls we get, like an acid chloride, an aldehyde, a ketone, an ester, and an amide. And it turns out the more reactive the carbonyl compound, the more 1,2 addition we will get. So an acid chloride is incredibly reactive, and so it means that when we add nucleophiles to this, it'll prefer to go 1,2 or add to this carbonyl. Aldehydes as well almost always like to react at the aldehyde, not at the unsaturated system. Once we start getting to ketones, now the nature of the nucleophile starts to play a much greater role, and we're preferring, depending on whether we've got hard and soft nucleophiles. And likewise with these over here, for instance, an amide is actually so unreactive at the carbonyl that almost exclusively we prefer a 1,4 conjugate addition. And so that wraps up the 3 factors. We're going to deal more with that in class, but I hope that this has just given you a decent overview of what we are going to be looking at.